Hi everyone, so today we'll introduce our project on multi-label music genre classification and generation using deep learning. As we all know, music is rarely confined to a single genre. Think of pop rock or jazz fusion. So multi-label classification is much more aligned with how we actually experience music. Traditionally, models like CNNs and RNNs dominated this space. For example, Choi et al. Used convolutional models on spectrograms, and Ponce et al. Worked with harmonic and percussive features. But more recent work, like the audio spectrogram transformer by Gong et al. In 2021, shows that pure attention-based models can outperform CNNs by capturing long-range patterns in audio more effectively. In our project, we thus implemented a transformer-based model, and we used Web2-Vec2-BERT model, which we'll explain in more details later. And before we get to the model, we'll first introduce our data first.
So for our project, we worked with the FMA small dataset, which includes 8,000 music tracks along with detailed metadata. We put out the key columns we needed, like track titles, genre labels, and train validation test split. One of the main fields we focused on was called genres all. It lists multiple genres for each track, but it was originally stored as text. So we had to clean and parse it into actual lists of genre IDs. Then we matched those IDs to real genre names using a separate reference file. To make the data ready for training, we converted each genre list into a multi-hop vector, a format where each genre is represented as a 1 or 0 depending on whether it applies to a track. After that, we analyzed how often each genre appeared and picked 22 that showed up at least 200 times. That gave us a good balance between variety and reliability. This clean dataset then is what we use to train our AI model. Then we feed our model with raw audio and use the processor that we debugged for processing it into the spectrogram, then carry on with further analysis.
For our model, we used Facebook's Web2-Vec2-BERT as our base model, and we fine-tuned it on 6,000-ish 30-second audio clips with multi-hop encoded genre labels. We kept the core of transformer architectures, but we replaced the lost original classification head with our own multi-classification layer, so that the final output layer has 22 output neurons. Then we implemented binary cross-entropy loss directly on the transformer's output logits, so that each output neurons make independent yes or no decision about the genre presence against our chosen threshold, which is 0.5. For the actual training process, we trained on thousands of raw audio clips, and during training, we implemented some functions to convert the raw audio clips into MEL spectrogram, and then feed the MEL spectrogram into the model. This is because the model is pre-configured to take the input as MEL spectrogram. And for the technical details of training, to fit the data into our NVIDIA L48 GPU, we trained our model on batch size of 2. This is because we have too many audios in one batch. And to compensate for the low batch size, we set gradient accumulation steps to be 4, so that the effective batch size would be 8. Also, we used mixed precision during training to further reduce the GPU load. For the optimizer, we chose AtomW with a learning rate of 5 times 10 to the power of -5, and weighted k equals 0.01 and set a linear decay scheduler. We in total trained 8 epochs, and each epoch has around 6,000 samples. And then for the evaluation metrics, we chose Hamming loss and F1.
And on this slide, we summarize our model's validation performance after 8 epochs of training with a fixed decision threshold of tau equals to 0.5. As you can see, the validation loss settled at 0.231, and the Hamming loss reached 0.0691. However, both F1 scores are 0. This happens because at the threshold of 0.5, none of the per general probabilities exceeded that cutoff. So every prediction collapsed to the non-label case, yielding 0 precision and recall. We can address this issue by turning the threshold. We evaluated thresholds from 0.05 up to 0.5 on the validation set and discovered the lowering tau equals to 0.05 enables the model to make non-trivial general assignments and can dramatically improve F1 performance. And our model has accuracy around 0.06. That's somewhat poor, but this is because we have only 8 epochs and train on small data set. At the same time, we have totally 22 genres, so it's very hard to get accurate multi-label prediction. And finally, we acknowledge several limitations for our pilot study. First, we trained on only about 6,000 samples, relatively few for transformer model. And second, we ran for just 8 epochs. So in the future work, we plan to expand training time and combine the generation model to our model. So thank you all.